The common emitter stage is like a water faucet that controls the flow of a river. The collector-emitter path is the river, and the base current is a tiny knob that decides how much water collector current flows. Biasing provides a steady set point so that the transistor stays in its active region, just as you would keep the faucet partially open so water always flows. The classic bias network uses two resistors R1 and R2, forming a voltage divider from the supply VCC to ground, creating a stable base voltage V sub B. The emitter is often given a resistor RE, which acts like a shock absorber stabilizing the operating point against temperature changes. V sub B equals VCC times R2 divided by open parenthesis R1 plus R2 close parenthesis. V sub E approximately equals V sub B minus V sub B E open parenthesis. V sub B E approximately equals 0.7 volts for silicon close parenthesis. I sub E approximately equals V sub E divided by RE. I sub C approximately equals beta divided by open parenthesis beta plus 1 close parenthesis times I sub E approximately equals I sub E beta much greater than. Choosing R1, R2, and RE so that I sub B equals I sub C divided by beta is about 1/10 of the current through the divider, gives a robust bias that is not easily pulled away by variations in beta or V sub BE. To understand how a tiny change in base voltage creates a larger change at the output, we replace the transistor with its small signal model, a set of linear resistors and controlled sources that work for small variations around the bias point. Key elements: R pi equals beta over Gm, the resistance looking into the base, where Gm equals I sub C over V sub T approximately 25 millivolts at 300 Kelvin. Gm times V pi, a current source from collector to emitter controlled by the base emitter voltage V pi. Ro, the output resistance due to the early effect, often very large, so it can be ignored for first-order analysis. The voltage gain of V is the ratio of the small signal output voltage at the collector to the input voltage at the base. Derivation: 1. The collector current I sub C equals Gm times V pi. 2. The collector voltage change V sub C equals negative I sub C times RC parallel RL. Negative sign because current flow creates a drop opposite to the input direction. 3. The input voltage V sub in equals V pi plus I sub B times R pi, but I sub B equals I sub C divided by beta. So the term I sub B times R pi equals I sub C divided by beta times beta over Gm equals I sub C over Gm equals V pi. Hence V sub in approximately V pi times 1 plus 1 approximately 2 times V pi for high beta, but the commonly used approximation ignores this factor, giving a V approximately negative Gm times RC parallel RL. If an emitter degeneration resistor RE is present, the gain becomes a V approximately negative Gm times RC parallel RL divided by 1 plus Gm times RE, showing how RE reduces gain and improves linearity. The input resistance R sub EI tells us how much the circuit resists a signal trying to enter the base. Without degeneration, R sub EI approximately equals R pi, which equals beta over Gm. With an emitter resistor RE, the resistance looking into the base is multiplied by the feedback factor. R sub EI approximately equals beta plus 1 times RE plus 1 over Gm. This can be visualized as a garden hose, the base, that now has a large tank, RE, feeding back some of the water, making it feel harder to push more water in. The output resistance R sub OUT is what the load sees at the collector. It is the parallel combination of the collector resistor RC, or the collector side of a load network, and the transistor's intrinsic output resistance RO, often a few hundred kiloohms to megohms. Thus, R sub OUT approximately equals RC in parallel with RO. If a bypass capacitor shorts RE at high frequency, RE does not appear in the small signal model, and the output resistance is simply RC, or RC in parallel with RL. These resistances are crucial for matching to sources or loads, and for setting the bandwidth. A CE amplifier behaves like a bandpass filter. It allows a middle range of frequencies to pass while attenuating very low and very high frequencies. Lower cutoff F lower is set by coupling and bypass capacitors together with the resistances they see. For a coupling capacitor C in at the input, the high pass corner is F lower in equals 1 over 2 pi times R sub in times C sub, in where R sub in is the source resistance plus the amplifier input resistance. Similarly, the emitter bypass capacitor CE creates a corner. F lower E equals 1 over 2 pi times the parallel of RE and 1 over GM times CE. The overall lower cutoff is the highest of these corner frequencies. Upper cutoff F upper H is governed by internal transistor capacitances C pi, C mu, and the load. Using the Miller theorem, the base collector capacitance C mu is multiplied by the gain, appearing as an effective input capacitance Cm equals C mu times 1 minus AV. The dominant pole is often at F upper H, approximately equals 1 over 2 pi times the parallel of R source, and R pi times the sum of C pi and Cm. Between F lower and F upper H, the gain is flat. This is the mid-band region where the simple gain formula of V equals negative Gm times Rc, or with Re, holds true. Analogously, think of a musical instrument that sounds clean only within a certain pitch range. Outside that range, the sound is muffled low frequency or tinny high frequency. P equals VCI times IC. In a common emitter stage, the collector to emitter voltage swings between roughly VCC minus IC times RC and a small saturation voltage. So the average power is about half the product of the supply voltage and the quiescent collector current. Thermal stability is achieved by using an emitter resistor Re. As temperature rises, IC tends to increase, but the increased voltage drop across Re reduces VBE, pulling the bias back toward the original point, like a thermostat that opens a vent when the room gets too hot. The safe operating area, or SOA, is a chart supplied by the transistor manufacturer that limits the simultaneous values of VCE and IC to avoid damage. When designing, ensure that the maximum swing of VCE and IC stays well inside the SOA boundary, typically by keeping VCE greater than VCE saturation plus margin, and IC less than 0.8 times IC maximum. Also provide adequate heat sinking. The junction temperature Tj equals Tia plus P times theta Ja, where theta Ja is the thermal resistance from junction to ambient. Keeping Tj below the rated maximum, often 150 degrees Celsius, guarantees reliability. The CE amplifier inverts the signal. A positive change at the base causes a larger negative change at the collector. This is because the collector current increases, producing a larger voltage drop across the collector resistor, which pulls the collector voltage down. Think of a seesaw, pushing down on one side lifts the other. Mathematically, the sign of the voltage gain of V is negative, indicating a 180-degree phase shift between input and output for mid-band frequencies. If a coupling capacitor is used at the output, it adds an extra 90-degree phase lag near the lower cutoff, so the total phase can wander between negative 90-degree and negative 270-degree depending on frequency. At very high frequencies, the internal capacitances introduce additional lag, progressively moving the phase toward negative 360-degree or 0-degree as you go beyond the upper cutoff. Understanding this phase behavior is important when chaining multiple stages, as cumulative phase shift can lead to oscillations. Design example - build a 10 kilo ohm gain CE amplifier with VCC equals 12 volts, desired mid-band gain approximately -20, and a quiescent collector current of 1 milliamp. Step 1, choose RC approximately VCC divided by 2 times IC equals 12 volts divided by 2 times 1 milliamp equals 6 kilo ohms. Use the nearest standard value 6.2 kilo ohms. Step 2, decide on emitter degeneration. To improve stability, pick RE equals 500 ohms. The gain with RE is a V equals negative GM times RC divided by 1 plus GM times RE. First compute, GM equals IC divided by VT equals 1 milliamp divided by 25 millivolts equals 40 microsiemens. Then 1 plus GM times RE equals 1 plus 0.04 times 500 equals 1 plus 20 equals 21. A V approximately negative 0.04 times 6,200 divided by 21 approximately minus 11.8. Since we want minus 20, we can bypass part of Re with a capacitor. Let Re total equals 500 ohms. Bypass Ce so that at mid-band the effective Re is approximately 0 ohms, giving a V approximately negative Gm times Rc equals negative 0.04 times 6,200, approximately minus 248, which is too high. Therefore, we select a partial bypass, split Re into 200 ohms unbypassed and 300 ohms bypassed. New gain of V equals negative Gm times Rc divided by 1 plus Gm times 200 equals negative 0.04 times 6,200. Divided by 1 plus 0.04 times 200 equals negative 248 divided by 9 equals minus 27.6. Slightly larger than minus 20, so increase unbypassed Re to 300 ohms, gives a V equals negative 248 divided by 1 plus 12 equals negative 248 divided by 13 approximately minus 19.1, approximately minus 20. Step 3 bias network, choose VE equals IE times Re total approximately 1 milliamp times 500 ohms equals 0.5 volts. Then VB equals VE plus VB, E approximately 0.5 volts plus 0.7 volts equals 1.2 volts. Use a divider that supplies 1.2 volts and draws about 10 times IB, where IB equals IC divided by beta. Assume beta equals 100, so IB equals 10 microamps. Divider current approximately 100 microamps. Choose R1 parallel R2 equals VCC divided by 100 microamps equals 12 volts divided by 100 microamps equals 120 kilo ohms. With VB equals 1.2 volts, R2 equals VB divided by VCC times R1 plus R2. Solving gives R2 approximately 12 kilo ohms, R1 approximately 108 kilo ohms. Use standard values 110 kilo ohms and 12 kilo ohms. Step 4 load line, plot IC versus VCE with endpoints VCE equals VCC. IC approximately 0, and IC equals VCC divided by RC approximately 12 volts divided by 6.2 kilo ohms equals 1.94 milliamp. VCE approximately 0. The chosen Q point IC equals 1 milliamp. VCE approximately VCC minus IC times RC equals 12 volts minus 1 milliamp times 6.2 kilo ohms approximately 5.8 volts. Lies comfortably near the center of the line, giving maximum swing. This completes the design. 1. Exam-style question, gain with emitter degeneration. Given a bipolar junction transistor with beta equals 80, VCC equals 15 volts, RC equals 4.7 kiloohms, RE equals 1 kiloohm unbypassed. The quiescent collector current is 2 milliamps. Find the small signal voltage gain AV. Solution outline. Compute Gm equals collector current divided by thermal voltage equals 2 milliamps over 25 millivolts equals 80 microsiemens. A V equals negative Gm times Rc divided by open parenthesis 1 plus Gm times Re close parenthesis. Gm times Re equals 0.08 times 1000 equals 80, which gives 1 plus Gm times Re equals 81. A V equals negative 0.08 times 4700 divided by 81 approximately negative 336 divided by 81 approximately negative 4.15. Answer approximately negative 4.2, gain magnitude 4.2, 180-degree phase inversion. 2. Exam-style question, load line analysis. Given same circuit as above, but Re is bypassed by a capacitor at mid-band. Tasks: A. Sketch the DC load line. B. Locate the Q point with IC equals 2 milliamps. C. Determine the maximum undistorted output voltage swing. Solution outline. A. Endpoints. Collector emitter voltage equals VCC. Collector current approximately 0 equals 15 volts. 0 amps and collector current equals VCC divided by RC equals 15 volts over 4.7 kiloohms approximately 3.19 milliamps. Collector emitter voltage approximately 0 volts. Draw a straight line between them. B. Q point. Collector emitter voltage Q equals VCC minus IC times RC equals 15 volts minus 2 milliamps times 4.7 kiloohms equals 15 volts minus 9.4 volts equals 5.6 volts, 2 milliamps. C. Swing upward until collector emitter voltage reaches VCC 15 volts. Delta V up equals 15 volts minus 5.6 volts equals 9.4 volts. Delta I down equals delta V up divided by RC equals 9.4 volts over 4.7 kiloohms equals 2 milliamps. Cannot exceed zero current. Downward swing limited by saturation collector emitter voltage approximately 0.2 volts. Delta V down equals 5.6 volts minus 0.2 volts equals 5.4 volts. Delta I up equals 5.4 volts over 4.7 kiloohms approximately 1.15 milliamps. The smaller swing is downward 1.15 milliamps. So the maximum symmetrical swing is about plus minus 1.15 milliamps in current or plus minus 5.4 volts in voltage. D. Output voltage swing equals plus minus 5.4 volts around the Q point. Total approximately 10.8 volts peak to peak. 3. Exam-style question frequency cutoff. Given coupling capacitor C in equals 1 microfarad, source resistance Rs equals 600 ohms, input resistance R in approximately 5 kiloohms. Find the lower cutoff frequency FL. Solution: FL equals 1 divided by open parenthesis 2 pi times open parenthesis Rs plus R in close parenthesis times C in close parenthesis equals 1 divided by 2 pi times 5.6 kiloohms times 1 microfarad approximately 28.5 Hertz. This illustrates how a larger capacitor or lower resistance pushes the low frequency limit lower, allowing more bass to pass.